It's just another late Thursday night on Earth. You're playing video games online while your girlfriend is doom-scrolling through a phone. A gaming rig, a slim smartphone, two different types of device in shape and size, but deep down both rely on the same fundamentals: electricity and programming. Every time you click your mouse and see your character jump or shoot on screen, you've just commanded billions of tiny electrical switches to work together in perfect harmony. But how does that actually work? Let's go back in time from the earliest concept of a computer. I'm Getz from Digi2X. Don't forget to like and subscribe. Let's jump right into it. So what is a computer? Believe it or not, the first computers weren't machines at all. They were people. In the 1800s, Ada Lovelace worked with Charles Babbage Analytical Engine and wrote the first algorithm ever intended for a machine. She even imagined computers doing more than math, creating art, for example. Fast forward a century, in the 1940s during World War II, 6 women became the first programmers of the ENIAC, one of the earliest electronic computers. They didn't have keyboards, they literally wired and rewired machines to make it calculate. Around the same time, Grace Hopper was creating the first compiler, a translator that allowed humans to write code in English-like commands instead of pure numbers. Before this, programmers had to speak machine directly by entering raw numbers or very cryptic codes. With a compiler, they could finally write something closer to plain sentences and let the computer do the hard work of translation. The term debugging already existed, but Grace pulling a mod from a malfunctioning computer was the first actual case of a physical bug. That little fella was creating errors in the calculations. By the 1960s, NASA relied on women like Katherine, Dorothy, Vaughan and Mary Jackson, calculating orbital trajectories by hand, the human computers who made the Mercury and Apollo missions possible. Allegedly, American astronomer John Glenn personally asked Katherine to double-check the electronic computer's math before trusting it with his life. From Ada Lovelace to NASA's human computers, we see a clear path. Computing evolved from human brains to electronic brains. Of course, humans can't keep up forever. To replace people, machines needed electricity, but not just raw electricity. The difference between electrical and electronic is that electrical is raw power, while electronic is controlling that power precisely. Think of electrical power like a river flowing freely. Electronics is the dam that decides when, where, and how water flows. Without it, you cannot reliably store data or run programs. And that brings us to the real heroes of modern computing: transistors. A transistor is essentially a tiny silicon switch with three parts: the source, the drain, and the gate. Imagine a faucet. Water comes in one pipe, the source, flows out another, the drain, and the handle, the gate, controls whether it flows or not. This on-off ability lets a transistor represent a bit, a 0 or a 1. When you connect transistors together, they form logic gates. A logic gate takes one or more input signals, 0 or 1s, and produces output based on a simple rule. AND gate output 1 only if all inputs are 1, or gate output 1 if any input is 1. NOT gate flips the input. If it's a 1, the output is 0. If it's a 0, the output is 1. These gates are the building blocks of all digital decisions, from adding two numbers to running entire operating systems, and therefore allowed the evolution of programming software. I'm a logic gates too, because I'm Getz and I'm logic. Before transistors, computers used vacuum tubes, glass bulbs that were huge, fragile and hot. ENIAC used 17,000 of them and filled an entire room. A big room, not like my tiny studio, I talk warehouse big room. In 1947, John Barden, Walter Bretton and William Shockley at Bell Telephone Labs invented the transistor, initially to improve telephone amplifiers. So the transistors were more resistant to damages, while having less electrical resistance. Suddenly, computers could be smaller, faster, cooler and more reliable. They later won the 1956 Nobel Prize for this invention. Today, your smartphone chip contains over 10 billion transistors, all working together to make your video games, apps and videos possible. It's like a tiny city of switches operating at incredible speed. A bit is really just a state of electricity. 1 means current is flowing, on, 0 means no current, off. So now that we know what a transistor is, how does it actually store a bit and keeps it from changing randomly? The answer lies in latches and flip-flops. One simple way is with a latch, two transistors wired together so they lock each other in place. Imagine two friends pointing at each other saying, "You stay up until I say otherwise." That creates a stable memory of 0 or 1 until one outside signal flips it. In modern chips, billions of these are packed together as flip-flops and memory cells. They don't flip unless the CPU or memory controller tells them to. That's why when your game is running, the data, your character's health, ammo and score, just doesn't randomly change by itself. The transistors are holding their state until an instruction says otherwise. That's where the clock comes in, a steady electrical pulse that tells transistors exactly when to update. And that's why processors are rated in gigahertz. Each tick of the clock is one step in the CPU's operation. 1 gigahertz means 1 billion ticks per second. To give you some perspective, our heart beats at 1 hertz, roughly once per second. A CPU at 5 gigahertz beats 5 billion times per second. Imagine your heart racing that fast. Your body would heat up so much, you'd be disintegrated. Processors come with a factory set clock, made to make sure it runs without physically breaking, but you can hack this parameter. That's what we call overclocking, increasing the clock speed, aka the frequency, to make the CPU perform more steps per second. That will void your warranty, so it's not a technical advice. More speed generates more heat, and the transistors can only handle so much until they get unstable and the computer explodes. That's why gamers invest in cooling systems. Of course, if the power goes out,
surprise, motherfucker!
Boom! All the bits stored in RAM disappear.
Please, no! No!
Because they were held electrically. RAM stands for Random Access Memory and is made for the CPU to access data faster. It's like a temporary cache that is close to the CPU, so the CPU doesn't have to constantly gather repeating data from the source. That's where a huge part of your OS, operating systems like Windows, macOS and Linux, is loaded to run smoothly. There are also cache systems embedded in CPUs, but I don't want to make it too complex for this video. And the fact that we need a place to store the data even when the computer is off is why we invented hard drives and SSDs. Memory that can keep its state without being connected to a power source, using magnetism and trap charges. If you want, we can get into more details in another video, but that's the idea. So we have bits, ones and zeros, and those bits and transistors live on circuit boards, which act like highways connecting all the components. The CPU is the brain executing instructions step by step. The RAM is the short-term memory, fast but volatile. The GPU or graphic processor unit is the artist, drawing graphics in parallel. And your hard drives and SSDs are the file libraries, so you can stop the computer without losing your game progress. Then come the peripherals, which are the input and output devices. A keyboard is an input device. It provides an entry point to the computer for your fingers. And the mouse is an input device for your hands. That's how we communicate with the computer. It's a low bandwidth, so some are trying to make the brain communicate directly with the computer. But it's not because you could that you should. Why? Because you could eventually fry your brain. An output device is a screen display or a printer. A touchscreen is both an input and an output device. Then we have the electricity source with either a power supply unit on desktop or a battery on laptops, tablets and phones. Each bit alone is tiny, but when combined they can represent letters, numbers, arrays, basically anything abstract like digital assets. One bit has two states, on and off, 1 or 0. 2 bits have 4 distinctive states. It's just not enough to code an alphabet or complex processes. For that, we need more combinations of ones and zeros. The formula to get the number of combinations available is 2 power n. 2 because we have 2 states per bit, and n for the numbers of bits. So 2-bit will have 4 combinations, 3 will have 8, 4 give 16 states, and so on. 8 bits make a byte. Scale up, kilobytes, megabytes, gigabytes, terabytes, petabytes, and you can now store a video game or even a large language model. We didn't get there in a day. The first gigabyte hard drive in 1980 was the size of a fridge and weighed 250 kilograms. Nowadays, your phone stores hundreds of gigabytes in your pocket. But humans can't write ones and zeros all day. That's why we invented programming languages. We have machine code, raw binary, ones and zeros directly executed by the processor. That's extremely hard for humans to read and write. Then you have assembly, composed of short mnemonic like move or add, still tedious but easier than pure binary. Then you have Fortran, the first widely used high-level scientific language in 1950s. It's still used today in fields like finance, engineering, and scientific computing. Banking is one of the most sensitive use cases. Imagine a bug that is mistakenly sending all the transactions to the N+1 account instead of the N account, or miscalculating thousands because of a wrong separator. Such an error could literally destabilize an entire economy. C, C++, and even C# are close to the hardware, used in most games and applications. Java, Python, JavaScript, and many others are high-level, human-friendly. There are many other languages, obviously, and funny ones like Brainf with only 8 commands. It looks like someone mashed up a keyboard. Whitespace is written entirely with spaces, tabs, and line breaks. To the naked eye, it looks like a blank file. In cow, every command is some variation of the word moo. So without going into complex algorithmic science, there are some basic building blocks that makes programs understandable. So the first part is the raw data, which we represent with variables. Variables can be a number like an integer or a float, a text like a chain of characters, strings, or HTML formatted text. Booleans are just binary 1, 0, or true or false. It's data, basically, in a particular format. Then we have conditional logic with if-else. If the player has a key, open the door. Else, well, nothing. Then we have loops, which repeat actions going through a dataset. In Silver Stripe, for example, you can loop throughout data objects and display, let's say, videos. And for each video, you display the thumbnail, title, and link the title to the original video. Another usual loop is the for each, which is the same logic. For each videos as video, display the thumbnail and so on. Then we have switch case, which has multiple options, and depending on the case, you will follow a certain path or action, like switch case, weapon type, sword, bow or gun, and the software will do an action depending on the weapon of the player. These are building blocks that you will see in most programming languages. Back to your game, you click the mouse, the CPU receives the signal, the program checks variables like player health, applies an if-else rule, and the GPU redraws the screen and the enemy flashes red. All of this happens in milliseconds. Your CPU is like a master conductor, coordinating billions of instruments at lightning speed, making sure every single note hits perfectly. Next time your character jumps on screen, remember, behind that action is a symphony of electricity, history, and code. A music beating at billions of pulses per second. Thanks for watching, see you in the next one, peace.